Hello. This is my presentation of my paper on cyclical pathfinding based on hierarchical shape analysis for use in a Sisyphus table toolpath generation. And here on the first slide, you can see my face and then the image that is produced by my algorithm after I run it on my face. So the initial question you're likely to have is, what is a Sisyphus table? And the answer is, it's essentially a two-axis arm that lives underneath a bed of sand, and it moves a marble through the sand to generate a pattern. As you can see here, it kind of looks like a Zen garden, and it's calming and kind of a luxury product. And so me and my friend were thinking about building one day, and I came up with the idea of what if I can actually make an image to go on this. I would like to be able to generate my own patterns for this out of a face, a flower, any photograph that I can imagine. So in order to do this, I need to be able to find all of the edges that are in that image. I need to find a set of points that approximate those edges, because just attempting to go through every pixel with the ball doesn't make much sense. There's no real order to where I would go when. It needs to be more of a graph-based approach. Then I need to find a cyclical path through all of those points that preserves the visual clarity of the image. This is a little harder than just using Dijkstra's formula and finding the shortest path through all of these points. I need something that preserves the visual characteristics of the original photograph. This algorithm does present several challenges. If I'm going to get any kind of decent resolution on this, I need 200, 300, or even more points than that. And finding a graph through that in the traditional method is pretty computationally expensive, so I'll need an efficient algorithm. My path needs to be cyclical, but connecting points at different parts of the graph is going to generate weird lines across my image that I don't want. And I'll need to figure out some way to group similar elements together so they get pathed together. So I'll show you what I thought of to attempt to implement this. So I came up with a few algorithms that I can use. To find all the edges in an image, I can use either canny edge detection or holistically nested edge detection. Canny edge detection has been around for years, since like 1985 or something. It's an analytical method of finding all the edges in an image and transforming them into very fine lines so you can use them in other computer vision aspects. It's widely used in industry. Holistically nested edge detection is a much newer thing. The paper was written on it by Xie et al. In 2017. It uses a series of convolutional neural networks, but it actually retrieves the output from each layer of the network to provide more training and more say on what the final prediction is going to be. You can see the sort of difference between the two algorithms there on the right. So for extracting the points from these edges, I'm going to use k-means clustering, which can distribute some centroids over a set of data points. For me, the data points are just going to be all the pixels in my image that are brighter than a given value. To form groups among these centroids, I can use border tracing and structural analysis, and then to find a path, I came up with my own weighted point selection algorithm.
Hi, so this is a demonstration of my edge detection and pathing algorithm for my Sisyphus table. So here in front of you can see my code. I can take you on a brief walkthrough of this. I have my code to run the DDA algorithm to determine the goodness of fit of a given line between two centroids. I have my scoring algorithm, which finds the weighted score between two given points. I have my pathfinding algorithm, which, based on a number of statistics, will find the best point to go to next to make it the most visually clear. I have my path merging algorithm, which is going to merge two groups together once I have pathed each of them. I have my k-means clustering, which generates all the points in the first place and groups them into their shapes. And down here I have my canny and holistically nested edge detection algorithms. So I run this from a command line interface. So I have a command I can input here, which looks like that. I specify the image and the number of centroids that I want, and it's going to go ahead and run holistically nested edge detection and generate my image for me. It should just take a few seconds. All right, my image should pop up on my other monitor here. in just a moment. There we go. All right. So this is what it looks like after the algorithm runs. And I'll make it a little bigger so you can see it. So you can see it delineates several different regions. There's a region of those orange centroids around my eye and the eyebrow above that. A region up in my hair, and it takes a piece of my hairline and my chin as well. Identifying these sort of visual regions and then drawing lines out to them and then coming back. So you can see those lines just sort of follow the natural progression of where you would expect edges to be in a photograph. There are some deviances, there are some lines that aren't going where they're supposed to, but the algorithm could use a little bit of bug squashing still. So yeah, that's it. I hope you enjoyed.
So, I hope you enjoyed the demonstration. These are my results. So as you can see, it has a runtime that's in usually the tens of seconds on a larger image, or sometimes a second or two on a small one. I tried it on a few different images. HED has a bit more of a start time than Canny detection, as one would expect. It needs to load the matrix into memory. On small images or things with few visual components, it actually works beautifully, exactly like I would hope. None of those lines that you may have seen in the demonstration. So for example, with this Apple logo, it's able to separate the leaf and the apple as different components. You can see that because the centroids are colored differently, the orange versus blue centroids, and then it connects them with the two closest centroids having a single line between them. So this would make a perfect toolpath for a Sisyphus table. On more complex inputs like this, like my face, the algorithm struggles a little bit, but as you can see, it's still able to delineate a lot of visual cues. It takes my whole hairline here, it finds my mouth and my nose and draws a line down to it, and gets the general outline of the figure in a recognizable way. As I mentioned, there are some issues that I am attempting to resolve as we move forward. I intend to introduce a criterion to prevent lines from crossing across white space too aggressively. The DDA algorithm is meant to do that, but it's not quite strong enough, so I'm thinking of using the shapes that I've extracted using topological structural analysis and ensuring the lines don't come too close into the range of those shapes. All right, well, that's my presentation. I hope you enjoyed, and thank you for listening.